Okay, so I want to show you a few things about higher derivatives, 3.7. A lot of this we've already learned as far as what the first derivative, second derivative means, but we'll kind of review that a little bit. So let's go ahead and go to the first example. We have x squared plus y squared equals 1, and we want to find y double prime. So first thing is we need to find the first derivative. So we're going to go ahead and say this would be 2x and then plus, and then we have 2y prime, and then on the right side, of course, that would be equal to 0. So that now we're going to isolate our y prime. So we have 2y prime equals negative 2x, and y prime would equal negative 2x divided by 2y, and so y prime would equal negative x over negative y. So that's our first derivative, and now what we need to do is find the second derivative. So we just find the derivative again. And so we say y double prime equals, and we use the quotient rule. So we're going to say low. So we have low, and then d high, which would be negative 1, minus high, which is negative x, times the low. And all of that is over the low squared. So that's all over y squared. Okay? So we'll probably do a little bit of a cleanup with that. So let's say that would be the same thing as y double prime equals, maybe just say negative y, and then probably a plus x, y prime. And unfortunately, I'm having a little trouble with this little guy. And then over y squared. Okay, so that's at least what we have for y double prime. But we've got a y prime in there. So now what we're going to do is, if we have a y prime that's in there, we're going to go ahead and replace that with what we know y prime is. So I'm going to go ahead and just finish it up here. So I'm going to say y double prime equals, and I'm going to go ahead and just start substitute the y prime there. So I got, so far I have negative y and plus x, and then this is where I'm going to put the y prime, so I'm going to put the negative x over y, and then all of that still over the y squared. Okay, so I'm going to do a little bit of algebra here. First step, I'm going to go ahead and just say this would be, just to clean it up, I'm just going to say wow, still having troubles. So I have negative y minus, and it's x squared over y squared. And what I'm going to do is I'm going to multiply top and bottom by something that will get rid of all these fractions. And what will do it is y over y, and I'm going to multiply just the whole fraction by y over y. So that will equal, it'll be y double prime equals, if I multiply the top by y, then what that would do is, wow, this is getting a lot of trouble. So I multiply that, and then multiply the bottom as well. So the bottom, I'll just do that one first. So the bottom is going to be y cubed, and the top is going to be minus y squared, and then minus, and then what that'll do is that'll get rid of the fraction. That's the whole reason why we do it. So then we have this. So we have minus x squared. Okay. And then what we could do is we could factor out negative sign out of the top. So I'm going to factor out a negative 1. So that would be, I could say y squared. I'll just say y squared plus x squared. And then on the bottom, it's y still. And then you might remember that the original problem says x squared plus y squared equals 1. So we can actually replace that with y squared plus x squared here. So we're going to go ahead and replace that. So our final best answer would be replacing this quantity right here with 1. So that's why it would be negative 1 over y cubed as a final answer. Okay? And that would be it for that example. And the next example, just to make this thing we talk right. Next example, okay, is let's say this is application of motion. So let's say we've got a function. It's s of t. S of t, I'm assuming this thing is going to work for me. S of t, and it equals t cubed minus 6t squared plus 9t. And what this is this is t, it's going to be in seconds, and the s, that's in meters. Okay? So if we wanted to find the velocity, then of course we just take the derivative. So velocity equals s prime of t, and that would be 3t squared minus 12t, and then plus 9. And then if we wanted the acceleration, then you guys know the acceleration would be the derivative of that. So that would be s double prime of t equals 6t minus 12. So we got the acceleration. And then there's also something else that's called the jerk, and it's when your rate of change, so the rate of change of your acceleration, and that's s triple prime of t, and that would be 6. And that's if you have like a mom like mine that, you know, constantly changing the acceleration, it kind of drives kind of a little jerky, like kind of erratic. Your neck kind of goes back and forth. That's what we're talking about there. Okay. The one other piece to this is that you really want to know graphically what's going on, and so I want to see if I can get the calculator out. So let me see if I can get this. Here we go. So if I can get the calculator. Here we go. So the calculator has graphed these same functions you can see in there. And so what I want to do is I'll highlight, you know, just the first one so you can see what the graph looks like. So graph that. That's what the graph looks like. I'll make it a little bigger here, but okay. So that describes the motion. So okay. So then we would look at the derivative. Actually, let me back up and kind of describe the motion. So what do you think is happening there? We're going a certain distance. It looks like we're going a certain distance, and it looks like we actually come back. I think we may have looked at this one before. I think we did. And then, so let's look at the second derivative. And highlight that again. And so just some key spots again, you know, where you've got a spot right here where the derivative would equal 0, and so you want to be able to identify that it's obviously right there. And then again, this spot here when it levels out, you can tell that's when the derivative or the velocity equals 0. So some of these key spots. And then similarly, when we look at the third, or the acceleration, the second derivative, so graph that, and you should be able to tell, when you look at 3 graphs, you should easily be able to tell which one's the position function, which one is the derivative, which one's the velocity, you know, and then which one's the acceleration. So again, you can see kind of a key spot here when the acceleration equals 0, it's right there. You can see that's when the rate of change of the velocity is equal to 0, right there. So right below that, my pen was cooperating. So I think that's pretty decent. We should be able to tackle the 3.7 homework when you come in. All right, later.